Okay, so today I'm gonna talk about Margrabe's formula, which nicely demonstrates how to use numeraires in quantitative finance. Uh, because there is a trick with change of measure, and here we are going to use different measure than we use in Black-Scholes, where the numeraire is chosen to be risk-free asset, which is money market account or bond. So in this case, the numeraire chosen won't be a risk-free asset, it will be a share. Let me just simply describe the payoff of an exchange option. Okay, so exchange option allows you to exchange one share for another. Say there is share S2 and S1, and you are allowed to exchange S1 for S2. Okay, so if at the maturity S2 is more valuable than S1, you get the difference basically. Okay, so that is what this payoff is trying to tell you. Okay, so this is the call option that allows you to exchange one asset for another. This is asset that pays no dividends. Okay, both S1 and S2. And I'm gonna set up a pricing equation or derive. Well, the first thing we have to do is to set up a risk neutral pricing formula, which basically says that at time of 0 the value of the option with respect to some numeraire, which will be in the denominator, must be equal to risk neutral expectation that is given by the numeraire of the payoff. Okay, of the payoff divided by the numeraire at the maturity. So in this case, I'm gonna choose S1 numeraire. Okay, because in this case it will really facilitate all the computations and the derivation of the formula. If we instead chose, say, a risk-free asset, the derivation would be much more complicated. Okay, so like I said before, the risk neutral valuation formula says that at time 0 it can be times t, small t, but for simplicity I use 0. The value of the numeraire, which is the stock 1 at time 0, must be equal to some risk neutral expectation which is bounded to this asset of the terminal payoff, which is this. Maybe I should choose these brackets. This is more common. Divided by the value of the numeraire at times t. Okay. Okay, so I get something like this, and now I will simplify this expression. I'll put this guy to the right hand side, and here I'm gonna divide divide the numerator by the denominator. I can do that because 0 divided by some non-negative or some non-zero number is 0, and those two guys I can also divide. So here I'm gonna have maximum of, say, number z minus 1, and that's all. Okay, where we have to, maybe I should use this notation, where z of t means that it's s2 divided by s1. Okay. The problem is that we have no idea what is the dynamics of zt whatsoever. So we cannot set up the expectation. The first thing is that we have no idea about the real world behavior of zt, and therefore we also do not have notion about its behavior under risk neutral measure, which is this sign, okay, this expectation under the risk neutral measure. Well, before I start to do some more, I should define the motions of S1 and S2. So it's clear that it comes from well-known differential equation. ds of t is equal to some drift of the first stock times the value of that stock times small shift in time, which is denoted by dt, differential of time, times some volatility term times the value of the stock at time t times Wiener process, Brownian motion, the differential of the Brownian motion. Okay, so this part is, well, deterministic in some sense, and this one is random. Okay, and similarly I introduce the motion of the second stock just like this, and one important point I have to pose here. Usually the stocks or the motions of the stocks are correlated. Okay, they are not independent. So I assume that there is some correlation rho between those two Brownian motions. Okay. Well, we now want to focus on the dynamics of z of t, because we know that it somehow comes from this relation, and we have specified both the motions. So we firstly derive the dynamics of this zt under the empirical measure, the real world measure, and subsequently we'll somehow transform it to the motion under the risk neutral measure. Okay, so to capture the dynamics, we will use the differential form. Okay, and from Ito's lemma, from Ito's quotient rule, we know that dz of t with respect to that of t is equal to differential of S2 divided by S2 times t minus the same for S1 minus product of these terms minus this guy squared. Okay, and we now we can now substitute for these terms, and let's see what happens. So this is equal to, and now if we put these terms, these s terms, to the left hand side, we got the differential with respect to s. Okay, so for the first case it will be mu1 dt plus sigma 1 differential of the Wiener process of the first stock minus basically the same just for the second, for the sorry, that should have been the second stock. Okay, just like this, minus minus the product minus, and now this guy squared. Okay, so if we square this term, we get sigma squared, sigma 2 squared. That's for the first stock. So if we square this, we got sigma 1 squared times dt. Okay, that's the famous result of stochastic calculus, that these terms go out and you only have part of the stochastic piece, but instead of dw you get the dt. Okay, so let's somehow regroup this. So there is, I don't like this behavior of the math type, but I cannot do anything with that. Okay, minus these guys at the end. Okay, times dt plus, let's focus on what happens with this term. Well, so this guys, this one times this one is 0. This one times this one is also 0. This one times this one is 0. This one times this one is rho, is the correlation, times sigma 1 times sigma 2 times dt. Okay, so I can put it directly in here. Okay, so that was that, and what remains are the diffusion terms over here. So put here this one and this one. Okay, so now I have a slightly better expression, but I'm not that much clever from this, because what I really hate is these two Brownian motions. To get rid of that, I can somehow merge them together. The trick is that this number, say it's random number x2, is normally distributed with zero mean and variance of sigma 2 squared dt, and this one over here, let's say it's called x1, is also normally distributed, but just with different diffusion term. Okay, and x2 minus x1, well, it's just difference of two normally distributed numbers, and difference of two normally distributed numbers is also normally distributed number, say x, which is in our case normal with zero mean and diffusion term, which is equal to sigma 1 squared plus sigma 2 squared minus 2 rho sigma 1 sigma 2 times dt. Okay, so let's call this one let's make a square root. Let's call this one sigma. So this one is actually n0 sigma dt distributed, sigma square dt distributed. Okay, so knowing this, we can create an artificial new Brownian motion expressed in terms of this sigma. So instead of this, we just use sigma differential of Wiener process. Okay, so those guys are substituted with this expression. Okay, well, we know that under risk neutral measure this term must be 0, because under risk neutral measure this term must be martingale. Okay, and martingales are driftless. So we need to invoke Girzanov theorem, and we define Radon-Nikodym derivative in the following way. We take this term, we divide it by sigma times dws minus 1/2 of integral just one more thing, there should have been minus in front of that, so here is gonna be this one squared ds. So that's the Radon-Nikodym derivative. Okay, and we know that the transformation kernel is equal to this term, and we also know that from the change of measure theorem, the Brownian motion under the empirical measure is equal to Gerzanov kernel times dt plus some new Brownian motion under risk neutral measure. Okay. Maybe I should write it like that. It really doesn't matter. Whatever you prefer. Okay. Fine. So if we plug this guy in here and we substitute for this function in here, we actually kill the drift. Okay, so dz to z, dz to z equals this one, or I could rewrite it like that, doesn't really matter, times and here comes this term. Okay, so when we multiply this term by this, we multiply by dt, we got exact opposite of this because here is minus and we kill the drift here. Okay, and what remains is the Brownian motion term under the risk neutral measure. Okay, so times sigma, so it's sigma times the Wiener differential under risk neutral measure. Okay, so this is the behavior of that, which is the ratio of two stocks under risk neutral measure. Okay, so this is what we actually wanted. We now want to know the distribution of that, so we can actually re-express this as times this term, and we guess the solution. I think it might be exponential solution. It's very similar to stock motion in Black-Scholes. Okay, so what I do is that I guess some y is equal to logarithm of that t. Okay, and the differential of y according to Ito's lemma will be differential of y with respect to z t times, or that should have been written the partials, times dz of t plus differential of y with respect to t times dt plus 1/2 second partial with respect to squared times this term squared, differential of quadratic variation. Okay, so now I'm gonna tackle this equation. So this equals, and let's first focus on the first one. So differential of y with respect to z, so it's 1 divided by z of t. So it's 1 divided by z of t times the differential, and it's actually this. So the first term is this. I forgot to say that we keep t constant, so this one is also 0. And from the third I get second derivative of y with respect to z, which means that it's gonna be 1 divided by z, and once again the derivative of that with respect to z, so it's gonna be minus minus 1/2 1 divided by squared times the differential squared. dy is equal to these terms, and let's focus on this guy. So this is actually the differential squared, so it's sigma squared, it's minus 1/2 sigma squared dt. Believe or not, it's like that. And since this one will actually represents the logarithm of z, this means that differential of the logarithm is equal to this, which means that zero times e to the into this term plus the noise. Okay, so this is the solution to this equation. Okay, so when we know this, we can actually try to tackle this equation. So I can rewrite this once again, and instead of z, I will use slightly different approach. Instead of the maximum, I'll use slightly different approach. I'll rewrite it using indicator functions. Okay, so the expectation remains, but we can rewrite the maximum as this one times indicator of z t greater than 1. Okay, which means that if z of t is greater than 1, then this function has a value of 0, and we focus on this area. Okay, it basically replicates this maximum. Okay. I can, however, rewrite this term. I can divide the... firstly, what I do is that I distribute the indicator function, so it will be like that and like that. This, however, doesn't make sense, and I keep only these terms. Furthermore, this is equal to 0 times expectation of the first term minus expectation of the second term. Okay, but the problem is, what's the value, or what's the expected value of this? This one is easy. It's just the probability of zt is greater than 1, and since we know the motion of zt, it's easy to evaluate. But this one is more demanding. Well, let's focus on this one. So let's just split the area and now focus on this one. Well, there is one important result of stochastic calculus that says that if we have some Radon-Nikodym derivative, this gives us new measure. The expectation with respect to Radon-Nikodym derivative sets up a new measure. The new measure will be denoted, well, I cannot get yeah, this is what I wanted. Let's say this is the new measure. Okay, so I got the expectation of the same, but under the new measure. Okay, expectation of the same thing under new measure. Well, I would like to misuse or use this this variable here to somehow transform the measure. Well, if I use the variables at t, I say this is equal to this will give me the following representation. I just take this, and instead of small t, there is a mistake. There should have been t. Okay. Okay. Doesn't matter. That's fine. So I would get this. But the problem is that I have this z0 and the Radon-Nikodym derivative, which is previously mentioned here. There is no such term. We only have two integrals. One is with respect to the Brownian motion, and the other one is with respect to time. Okay, so here I have here I have basically the same representation, but the problem is this this constant. So instead of z of t, I introduce z of t with respect to z0 and this will give me the following thing. Okay, and now we can basically identify the Radon-Nikodym derivative where the kernel is sigma. Okay, using this representation, I can introduce new Brownian motion under this measure, which is defined as follows. The original Brownian motion under a risk neutral measure times the kernel, which is sigma, times dt, plus the differential of the new Brownian motion okay. So I basically have a new dynamics for z under this measure. So instead of this term, I will use these terms, so it will result into positive sigma. Okay. Okay, fine. But still, I haven't tackled. I still haven't got to this term. Okay, I'm still over here. So let's go on. And I know that I want to put that I want to put L of t over here. So in order to do that, I must factor out this one, then I can put into the bracket this one divided by z0, because these two are equivalent, and I also know that this one is the Radon-Nikodym derivative. Okay, so this will give me this expression, which is, according to this relation, exactly expectation of the indicator under the new measure. Okay, so this is really very tricky. It's very handy, the measure transformation. So what I have here is solution for this term, which can be plugged into in this place, and I have some more term over here. Okay, so let me just put this down, and this one will be substituted with this expression, and the other one I'll keep. Well, what's the expectation of indicator function? It's the probability of the event to happen. So that means that it can be expressed has a probability that this event will occur. Okay, and likewise minus probability of the under the risk neutral measure that this event will occur. Okay, and notice that we have already defined the behavior of zt under this measure, which is defined in here, and also we have defined the behavior of z of t under the risk neutral measure, which is in here. Okay, these two, you can see that the Wiener process has the same sign as this thing. Okay, so I'm gonna now focus on the solution of this term. So when z of t is equal to 1, is greater or equal to, is greater than 1, it's the same under this measure as if this expression is greater than 1. Okay, now I can divide by z0. So it's gonna be 1 divided by z0 and take logarithm. So it's gonna be okay. I just rearrange this. I keep this one on the left hand side and move the rest to the right hand side. I forget to use the big T, but it's not a big failure. It's just few changes. Okay, that's it. Now I'm gonna multiply by -1 the whole expression. What it does is that it puts here this one, and also we have to change the sign. The right hand side here we have to change logarithm and sign. Okay, now we can divide by sigma. So the left hand side, I don't like this notification. Let me just erase something so that I can continue. Well, tell me something which is useless. Okay, we will erase Ito's lemma. Okay, fine. So it's less than this expression. Divided by sigma. We are still not that smart from this expression. It doesn't tell us anything. Notice that we are in fact solving the probability. Of this event. But what's the distribution of this? Or the whole thing in here? Well, the distribution is by definition normal, zero mean, and variance of t. That means that in fact, if we denote this term over here as d1, oh sorry, I forgot one important thing. Yeah, sir. Nothing. This is fine. So it's the distribution normal with variance t. Okay, but we can standardize it, however, just by dividing square root of t. Because this expression here is a random variable which is normally distributed with mean 0 and 1 variance. Okay, so basically this is the probability of normal variable being less or equal to something which is given, and let's name it d1. So this is basically ND1, where n is a standard normal cumulative distribution function. Okay, that means that in this expression we have this. Okay. And in the similar fashion, we can solve this one. It's not difficult to evaluate. We have the dynamics over here. So here's the dynamics of that. This is the probability. Ah, sorry, it's actually here. Okay, so we are solving this probability. So we are interested in the probability of this to occur so in the similar fashion. It means that we can divide 1 by, okay, again, yeah, I know, okay, so let me erase something, maybe this part. Okay, you take the logarithm, which means that we have on the right hand side we have logarithm of okay, so you regroup. On the left hand side we only keep this one, on the right hand side we keep the rest, and that's it. Now we are going to divide by or multiply by -1. This means that minus is less or equal to again okay. Now I divide by sigma and square root of time, so this means that on the left hand side I have on the right hand side there only remains times square root of time and since we are solving the probability I forgot to divide by the square root. This is again normally distributed. It's a standard normal. Let's call this expression d2. So this means that it's n d2, where n is cumulative standard normal. So the formula for the option price finally takes the form sometimes this application is stupid. Oh, please let me finish it. Yes. And notice what is Z0. Well, Z0 is S2 as of time 0. Let me just... Oh no. Do you think I can finish this example? Okay, what can I delete? Okay. This should be enough. That at 0 means that it's 0 and so it's like this. That means that which means okay. Where d1 is defined with this expression where Z0, as I said, this. And E2. Oh, please. Okay. So this is finally the solution to our problem. Okay. However, to make it the same. Okay, so this is the so-called Margrabe's formula to exchange one asset, one share, for another one. Okay, many of you can for sure identify pieces of Black-Scholes. In my previous video, I've shown you how you can derive Black-Scholes formula. Unfortunately, without sound, so I might create the video once again. So thank you for watching my video on how to work with numeraires, and to visit my channel again.